Good morning. Sorry. Good morning, everyone. I'm Geonsun Lee from Korea University, and today I'll be presenting on behalf of our team our work, Obstacle Detection and Alert System for Smartphone AR Users. So without further ado, let's get right into it. With the recent prevalence of AR, you might encounter such situations where you are extremely concentrated in an AR game that you are not really aware of an obstacle ahead of you, resulting in such hazardous accidents. So to prevent such situations, we propose a technical solution called Safe AR, which is an obstacle alert system for pedestrians using AR applications. And this system only uses the rear camera of a smartphone without any additional sensors. Our system first detects obstacles within the field of view of the smartphone's camera. The current implementation utilizes Google AR Core, which is a platform for visual inertial odometry. And this returns a set of visually distinct 3D feature points. And an example would be the figure on the left, which is a picture of a corridor. However, it is notable that not all of these feature points are necessary for obstacle detections. For example, the feature points on the ceilings or the side walls are not really necessary. So, therefore, we define the region of interest to discard such unnecessary feature points. The ROI is set to 3 meters by 1 meter by 3 meter. And it is notable that we included 2 meters below the smartphone's location so that the system can also detect downward staircases or downward curves. Next, RANSEC is applied to the feature points to identify a reference plane, which mostly corresponds to the ground or the floor. A feature point is determined to belong to an obstacle if it's above or below the reference plane by 10 centimeters. Of course, this threshold is empirically determined. And moreover, we consider the frontal area unsafe if there are more than a certain number of obstacle features. This is set to 3 in the current implementation. In the video, the reference plane is visualized as green when it is safe. But as soon as an obstacle feature is detected, the reference plane turns into red, indicating that the frontal area is in fact unsafe. Now, we conducted a validation test with the shown 8 daily obstacles, a cube, cubes stacked in 2 and 3, a wall, and upward and downward staircases and curbs. So one of the 8 obstacles were placed at the end of a 12-meter long path, and 7 volunteers were instructed to walk down that path while using our obstacle detector. The figure visualizes the part of the obstacle features, and the detection performance of our obstacle detector was successfully validated not only for those that are vertically high, such as those cubes, walls, and upward staircases, but also for those that are actually low, such as the downward staircase and the downward curve. Now, let's get into the actual experiments. We made 2 experiments with the obstacle detector. Experiment 1 was conducted to find interfaces that most effectively alerted users while least disturbing their AR experience. And again, experiment 2 was conducted to find interfaces that most effectively guide users to hold their smartphones with the desired orientation. This orientation is an important factor for obstacle detection, and we'll talk about this in more detail soon after. Finally, we developed a prototype based on the results of the 2 experiments. We tested this prototype application to investigate its usability. In our experiments, the subjects were instructed to play an AR game while walking. We thus developed a very simple AR game where the player should touch the appearing target when the shrinking red outline matches the targets. The gameplay would look something like this. So, there were 2 difficulty levels for this game, and the targets appeared faster at a higher level. As aforementioned, the first experiment's goal was to find interfaces that most effectively alerted users. So 20 subjects were instructed to walk down a 90-meter outdoor straight path while playing the AR game that we just presented. There were 3 obstacles, 1 cube, 2 cubes, 3 cubes that were placed randomly on the path, and then the subjects were asked to touch the OK button on the upper right part of the screen as soon as they recognized any obstacles. For user safety, of course, the obstacles were made out of safe, soft materials, and the users walked around the obstacle when detected. So we compared 3 common modality alert methods. First up is visual. So as soon as an obstacle is detected, the screen turns into translucent yellow, and at the upper bar there appears a warning icon. As for auditory, as you can just hear now, there is a siren noise repeated. And for tactile, sorry, I didn't expect this to be so loud, but yeah, a vibration is provided. And for no alert, there is literally no alert provided to the user. So let me present the results of experiment 1. First, we analyzed the detection time differences for each alert method. This is defined as the time when the user touches the OK button minus the time when our system detects an obstacle. Since the former actually indicates the moment when the user notices the obstacle ahead of them, this means that the higher the DTD, the later the user's detected obstacles than the system did. In this sense, if the DTD is closer to 0, this means that the subject's reaction to the obstacle was almost simultaneous to the issued alert. Now, as for the results, for both difficulty levels, No had the highest DTD, meaning that the other 3 common modality alert methods were actually effective and contributed to the obstacle avoidance. So, yep. And auditory and tactile showed the lowest DTD for both levels. And finally, No was the only alert method that had significant difference in terms of DTD when it came to obstacle sizes. This means that the other methods were generally effective regardless of the size of the obstacle. Next, we analyzed the miss ratio. In the AR game, it is a miss if the target is not touched before it disappears. This ratio represents how concentrated the users were in the AR game. It turned out that visual, auditory, and tactile were the lowest, had the low miss ratios than No, while tactile had the lowest miss ratio. This means that tactile is the interface that least interferes with the user's AR experience. As for user subjective evaluation, we asked which alert interface they preferred the most, and auditory and tactile were the most preferred. In conclusion, auditory and tactile were identified as the most effective alert interfaces. Next up is experiment 2. Understand that the obstacle detector's performance is highly dependent on the orientation that the smartphone cameras are held. The figure on the left shows that the holding orientation indicates the angle between the walking direction and the camera's view direction. If the camera is held too high or too low, the environment won't be properly examined. Hence, we should find interfaces that most effectively guide users to hold their smartphone with desired orientations, which in this experiment is set to 40 to 50 degrees. The subjects were instructed to walk a 90-meter long outdoor path while playing the AR game again, but this time there are no obstacles placed within the path. We compared different orientation guide interfaces in the experiment, which I will be shortly be introducing in the next slide. So, we implemented 6 orientation guide interfaces. Once the orientation is out of the predefined range of 40 to 50 degrees, instructions are provided to the users. First up is visual guides, and first, for a brightness guide, the brightness of a sub-area of a screen is changed to guide the users to tilt their smartphone to a particular direction. We also have pointing guide, where a yellow arrow is appeared on the upper part to guide tilting directions. As for auditory guides, there are abstract auditory guide with a siren noise, and also specific auditory guide where a recorded voice of up or down is played back.
Down, up.
Pretty straightforward. And there is also tactile guide, which also provides the vibrational feedback for both directions, and no guide, where no instructions are provided. Now let's see the results. First and foremost, we measured the total time the holding orientation was out of the desired range, denoted as TO. As seen in the figure, brightness, pointing, and specific auditory guide had the lowest TOs. This actually indicates that the interfaces with directional information were generally more effective. As for miss ratio, brightness guide had a significantly higher miss ratio compared to that of no guide. And in the aspect of subject evaluation, specific auditory guide and pointing guide scored the highest in terms of convenience, effectiveness, and preference. Pointing guide and specific auditory guide are thus identified as the best interfaces for guiding users holding orientation. Now lastly, we conducted an application test. Now let's make a quick recap. In experiment 1, we found that auditory and tactile were the best interfaces for alerting users of obstacles. Next, in experiment 2, we found that pointing guide and specific auditory guide were the best for guiding holding orientations. With these 4 interfaces, we defined 4 combinations, the combination of auditory and pointing guide, auditory and specific auditory guide, tactile and pointing guide, and finally, the combination of tactile and specific auditory guide. Combining the findings experiment 1, 2, and our obstacle detector, we developed a prototype system named SafeAR. For the application test, 30 subjects were instructed to walk down a 120-meter indoor path with 2 floors, as depicted in the figure on the left, which had 6 obstacles. So, a swivel chair, and a flower pot, 2 upward staircases, and again a swivel chair, and finally a display board. So a subject performed a trial for each combination, resulting in 4 trials in total. We surveyed usability, immersion, preference for each combinations, and subjects' intention to use for the whole system. Now, usability was measured through a system usability scale, and the results revealed that there were significant differences between the combinations. While the combination of tactile and specific auditory guide scored the highest. We also asked subjects a few questions regarding immersion and distraction. For example, Q1 asked whether they were fully immersed while playing the AR game. And for example, Q3 was asking the users whether they were distracted by any of their surrounding environments. The results showed that there were actually no real significant differences between the combinations for all of these 4 questions. Subjects also ranked the combinations in order of their preference. It turned out that the combination of tactile and specific auditory was the most preferred. Let's take a look how this would actually look in the real world. So the specific auditory guide and the tactile alert. We also find inspiring results regarding the intention to use. Before beginning the application test, we asked subjects whether they are willing to use an obstacle alert system while playing an AR game. This was answered in a 5 Likert point scale. And after completing the test, the subjects were asked to answer the same questions, but this time the results were significantly higher than before. Now, this indicates that users became more willing to use our system once they have actually experienced it. Finally, let me summarize and conclude the presentation. So we developed an obstacle detector for smartphone AR users and validated its performance using real-world daily obstacles. And through 2 experiments, we identified interfaces that are effective for alerting users and guiding users to hold their smartphones in a specific desired orientation. Then we combined the results into a prototype called SafeAR. And our user test proved that SafeAR is in fact very usable and effective, and users also expressed their intentions to use this system. We further envisioned that SafeAR can be ported to non-entertainment areas and non-AR areas, such as creating an obstacle alert system for the visually impaired. Now that would be the end of my presentation. Thank you so much for listening, and feel free to ask me questions.
So I have 2 questions. They are related. So the first one, did you have any unwanted side effects that people fell cybersick, or did you have some people actually bumping in objects or obstacles or tripping over or something like that?
Eventually, people all actually noticed the obstacles before they bumped into it, so there were actually no any accidents made in the experiments. And as for the first question, you were asking for cyber sickness. Since it is an AR game with actual no 3D objects and very plain 2D objects to be touched, there were no actual kind of sicknesses or such reported to us. Thank you.
Thank you.
Thank you for your presentation. I was wondering, did you quantify the energy you need for the different interaction? Like, does it consume more to have a vibrating or to have audio signal? Because you're on phone and embedded system, so maybe you need to quantify those quantities?
So regarding the battery consumption, which you're talking about, we actually really didn't quantify any of those because the main objective of our experiment was to just make a whole system actually integrating interfaces to alert and guide users. But it would definitely be important for actual practical use. Yes, I agree.
Okay, thank you.
have a question regarding the first experiment. So you have these different modalities, right?
Yes.
When you design this visual feedback, so you use this translucent yellow, right? But it seems that it kind of appears similar to the background. Maybe that is the reason why the scores was worse than other modalities. Like, did you try some other feedbacks, like for example red or some other colors?
Oh, so you're...
So is it is it optimal, you think?
So you're saying that yellow might not be the optimal color for alerting users, is that correct?
Yeah, because it's kind of consistent with the background.
Oh, I don't know how it actually appears in the screen, but in the actual test, it was fully visible. And the only reason that some missed ratios were lower than the other modalities was because that it actually interfered with their actual experience of the AR game. So I'm not sure if it would actually act differently with a different color.
Yeah, and another question is regarding the lighting conditions. For example, when you hold the phone and like outside, because of the sun, you cannot really see well the details like on your phone. What about in your experiments? So you perform some experiments outdoors and indoors, right? So did you consider the brightness?
For the brightness, we actually tested beforehand to make sure that all those interfaces are fully visible to the users. And I do agree if it's an environment with more dimming lights or darker, then it would actually not really be practical to use such brightness interfaces. But at least for our experiment, it wasn't really a problem.
Thank you for a great talk. I'm curious, I have a two-part question sort of. So the Safe AR system, is that targeted at playing AR games or just using generally with your phone?
The thing is that we were first motivated to create an alert interface for AR games because normally we would think that people will be fully aware of obstacles if you're like playing AR because the background is transparent. But what was interesting for us to see was that people were actually not really aware of what was going on the background. So yes, this is targeted for AR initially, but we actually received a lot of feedback that it could be better for just texting or just normal use of smartphones.
All right, so in continuation of that, it seems that the game you made was very visually intense. So it was straining the user or drawing on the user's vision. So do you think that is why the tactile and auditory feedbacks performed better? And how would you handle a game that has tactile feedback and auditory feedback as well?
The thing is that we had to conduct our experiment in a quite extreme case just to make sure these interfaces would be valid for any situations. But yes, I do agree that there are actually some user feedback that tactile can actually be misunderstood just like text notifications, and for example, auditory could not be heard if it's a very crowded environment. There are definitely some limitations, but for the experiment for now, that's what we have identified. Yes.
Thank you.
Thank you for your work. It was very appreciative. I'm curious about this work that can we use, or do you have any plans or solutions about the traffic light or a very fast object such like cars, not just the objects on the floor?
So you just mentioned the biggest limitations of our work because we are using Google AR Core, which is a visual inertial odometry platform, which means it only works for static objects, and it doesn't really work for moving objects, which is mostly the obstacles that we face day to day. So that is definitely what we're trying to do for our future work. Yes.
Thank you.
Thanks for the presentation. As someone who's tripped over playing Pokemon Go, I look forward to seeing this rolled out. But I was just thinking about when you're saying the positional angle, the 40 to 50 degrees for it to be most effective. Is that something that you foresee with a wider angle on the cameras at the front that might be able to be overcome so you can sort of limit the need for that adjustment? Because I'd imagine there is going to be variation in how people prefer to hold their phone.
That is definitely a viable point. We actually did our experiment with Galaxy S7, which doesn't really contain the wide-angle cameras that we have with recent smartphones. And the actual system works also for 30 to 60 degrees, but we just set the angle to be 40 to 50 degrees just to make sure the users can see the interfaces as often as possible during the experiment. So yes, in the future, I do agree that there would be some experiments regarding the wide-angle cameras.
I have a question. Was there any fatigue distinction between the haptics and the audio cues? The repeated audio, do you get bored of it or fatigued?
Our experiment was very restricted, so there are only 3 obstacles, obviously. So there were no really annoyance appearing to the users, but if it's actually done in a real-world environment where there are like a lot of obstacles, it might have different results.
Okay, let's thank the speaker.